You're good.
Yep. Hi, everybody, on this wintry day, a snowy day. It's a real pleasure to have with us today Peter Mucha. I looked up the pronunciation tip you gave us, just like Alphonse Mucha.
Yeah, well done.
So Peter is the Jack Byrne Distinguished Professor of Mathematics at Dartmouth. He went to college he was from Texas, raised in Minnesota, went to college at Cornell, where he studied engineering physics, then went to Cambridge for his master's in physics and came back and then was at Princeton for his MA and PhD. Had a 2-year postdoc period in MIT, then was at North Carolina Chapel Hill then was at Georgia Tech, then was at North Carolina Chapel Hill for a very long time, and then recently moved to Dartmouth. He has won numerous awards. I won't go through the list. He's also a sports statistician, but he's not going to talk about that to us today, I think. And instead, he'll tell us a lot about networks because he's been one of the leading people in this area for a long time. So over to you, Peter.
Wow. Okay. Well, thank you very much for that introduction, and thank you very much both for the original invite and then for the reschedule when I had to cancel on you last minute because of some illness last spring. I'm really happy to be here today, or here virtually. I guess it's a good thing I didn't try to get there in person with the storm you're all having. What I wanted to do today was tell you a bit of a story that stretches out over many years about community detection in networks, and in particular about how to take a look at the many different solutions that you might get running community detection in networks and how to pick parameters. And so this will be a very networks methods based talk, but at a very high level aimed at the user who wants to use this for their own data, not with any specialized networks pre-knowledge, and is just trying to use these kinds of tools in a good way to cluster their own data. So let's see, there we go. Okay, get the screen going forward a slide. All right, so the outline of what I'm going to try to do today is introduce you to an now old concept in network analysis called modularity.
Peter, we're not actually seeing your shared screen.
Oh, shared screen disappeared. Okay, let's...
I see it. I don't understand. I do see it.
I see it too.
Okay, sorry, my bad. I apologize.
Oh, good.
Please go ahead. It's all good.
All right, good. Good. Okay, so yeah, so I introduced you to a concept called modularity, an old concept, a bit of a troubled concept, but the most commonly used method of community detection in networks. Make a pointer to some uses of modularity in multi-layer networks, which might be of interest to a lot of this audience, and then step through a couple different concepts that have arisen in the last many years about how to improve results that are modularity-based for community detection in networks. One is a method of our own making that we call CHAMP. You need to have a good acronym for your method. We'll get to what that acronym is when we get there. An idea that was not ours, which was how this kind of network clustering of nodes into communities is equivalent to a particular kind of stochastic block model. Some work by Mark Newman and then some work by Mason Porter and his students. And then we're going to combine these two ideas into what we call pruning with parameter maps, or sometimes call iterative maps on the CHAMP set. This also includes, here's some links to some software packages that we have. We're really keen to have people use these kinds of tools and to help people use these tools. And of course, none of this work would have been possible without some generous funding from many different parts of the US federal government system for funding this research. So to try to make sense of what do I mean by community detection, I often like to start with this old example we worked on with a former student of mine. This hairball you're seeing right here is a force-directed visualization of a very small corner of Facebook at Caltech 20 years ago, in the early days of Facebook, back when you needed a .edu address to even be on Facebook. And so every one of the little symbols here is a node of a network representing users at Caltech. And the edges between them that connect the nodes, they indicate reciprocal friendships on Facebook. This hairball isn't probably terribly enlightening by itself, even though I've already strategically chosen the node colors and shapes here to indicate the house information volunteered by users in their profiles. That is, each user said where on campus do they live. And if you squint at it and kind of fuzz it out, it suggestively hints at the social role of where students live on campus, influencing the structure of this network. In particular, at Caltech, undergraduates join a house at the beginning of their first year, and they generally remain affiliated with the same house for the duration of their studies. So it makes sense that this would have a strong impact on the social relationships at Caltech. So if we run a particular community detection algorithm on this, what it does is a community detection, it gives us an unsupervised clustering of the nodes into communities. So this visualization is the exact same data, but now pre-processed using only the Facebook friend connections. I didn't use the house information except for in the visualization. What we're doing is we're placing each node into a community. That is, in particular, a community is going to be a group of nodes that are more connected to each other than they are to the rest of the network. And we're visualizing each one of the communities here by a pie chart, scaling the areas of the wedges proportional to the number of node users that have that particular house label. So again, the house labels aren't being used for anything other than divvying up the wedges in each of these communities. And the clear takeaway here is that indeed the house structure is exceptionally well aligned with the identified communities. If you look in the very center, the vast majority of the yellow users are in one Pac-Man shaped community in the center. Most of the darker orange is in the community to the right of the Pac-Man. If you look directly above the Pac-Man, there's a community that's broken up mostly into cyan nodes and red nodes. That actually turns out to be two houses that are right next door to each other on one end of campus. And the only color you see here that seems to be broadly distributed across the communities is purple. Well, purple represents the users who didn't volunteer on their Facebook page where they lived. So even without explicitly volunteering this information, though, the strong organization of the Caltech Facebook network along this attribute means you could make a pretty good guess for most of these purple users. I mean, if I were throwing a party for all of the members of the green-colored house, then I'd probably go out on a limb and invite the people in the purple wedge that's affiliated with that mostly green community. So the way that this was done here is with an old idea called modularity, which was introduced by Mark Newman and Michel Gervin more than 20 years ago. It's a descriptive objective function that we're going to optimize. It measures the within community edge weight of a partition of nodes into communities relative to what you would expect in some selected, hopefully appropriate random graph model. So here, when I say modularity, or sometimes I'll just use the word quality, I mean some variant of this kind of formula for Q, which depends on your data in the form of the adjacency matrix. So this Aij is just whatever data you have. A null model, this Pij, the most common null model, if you just look up modularity or you're just running a code that claims to optimize modularity, is it's typically a product of node degrees for an undirected network. So Ki and Kj here are respectively the degrees of nodes I and J. Together, we're going to call this combination a modularity matrix. There's lots of neat things in the literature about the spectral properties of this matrix. And so now the sum over the elements ij are being hit with this indicator function. So you're only really summing over the pairs ij that have been placed in the same community together. And so the optimization problem here is we want to find a partition of nodes. That is, it's a hard partitioning of nodes. So every node is going to get a community label into the communities to maximize this value Q. And the resolution parameter gamma here that's been snuck in was added to modularity by Reichard and Bornholt to control the number and sizes of communities. What I like to say, if you're just following the idea of this objective function at the loosest end, is if you crank up gamma, what you're doing is you're making this so-called null model piece more and more important. And you're paying a higher cost to put two nodes that aren't otherwise connected into the same community with each other. So as you crank up gamma, then what you're going to tend to get are a larger number of smaller communities. If you crank down gamma, then you're going to get a smaller number of large communities. And in fact, if you crank gamma all the way down to 0, this optimization problem is just how do I pick a partition of nodes into communities so that I maximize the total edge weight that's within the communities? Well, the easy way to do that is just take any connected component and call it a community. So that's the extreme when gamma is 0. Just to get an idea to see how this works in practice, and with apologies that multiple of my examples are going to be south of the border, I like to sometimes look at these, to look at the methods of community detection through some data sets that people have some familiarity with. And so here's 2 examples of thinking about how to cluster data from the US Congress. On the left, we have an adjacency matrix of voting similarity patterns. So this is a dense weighted graph because every pair of US senators who were present in this in the so-called 85th Senate in 1957 and 1958 are being connected to each other by a weighted edge whose strength is how similar are their voting patterns to one another. This is in contrast to the picture on the right, which is a different congressional example that we looked at many years ago, where this is members of the House who sit on committees in the House of Representatives. And so this is a network of the different committees and subcommittees of the House of Representatives that are connected to each other. Perhaps unsurprising, if you try to cluster the nodes that are the different committees and subcommittees into communities, what you find is you find the main committees, like the Appropriations Committee at the top. It's the square node surrounded by a bunch of blue circles, and all of its subcommittees, which are those circles in the same color. So you end up picking up the structure that there's a main committee and a bunch of subcommittees. With the voting similarity data on the left, what you can already kind of see here is I've already selectively ordered the senators in this adjacency matrix so that you can see the heat map, that it's just a lookup table of, Senator I by Senator J, how similar were their voting patterns. And it's, pretty close to a 2-party split, which is what you expect for most of American history. That's what it looked like in the late 1950s. That's during the era, the beginning of the so-called era of civil rights legislation. So it's not a particularly clean 2-party split. This is what it looks like for most of the 21st century. It's my team versus your team. So once upon a time, I was showing this to a good friend of mine who happens to be a clinician investigator, studies a lot of interesting metabolomics data for various biomedical applications. And he asked me, I think mostly with a straight face, what if the senators were E. coli bacteria? And if instead of voting on bills, they had different genetic virulence factors that would make you sick. And so sure enough, we were able to do a similar kind of analysis there, where every one of the dots here is a strain of a UTI-causing E. coli bacteria from a hospital in St. Louis, and the weighted edges between them are a notion of similarities between the two different identified samples. And so you can see that this clusters pretty cleanly into 3 big groups, red, green, blue, and then maybe this sort of outlier spread out black group. And much like the Facebook data, where we can do an unsupervised clustering and then see, are there interesting differences between the clusters, that is, between the communities, and sometimes I'll use the word groups. I kind of use all these words interchangeably. Here, if you look at the different communities that were found in this similarity network of genetic virulence factors, there are some key differences in the resistances of one of the communities to one of the 2 main bacteria, one of the 2 main antibiotics. And in another community, it's a different antibiotic that there's a large degree of resistance to. And so it's sometimes interesting to take our data, just like you do with any data set. This isn't, the big picture idea here isn't specific to networks. It's I have data and I want to cluster that data into groups where my objects have now been clustered in a way that I can see that they're more that groups, objects within the same cluster are more similar to each other, and then ask and probe the data for what's distinct about those groups. Continuing back to the Senate example, though, it's important to emphasize that what I showed you before were adjacency matrices for just two different two-year periods of the Senate. But of course, that's a temporal network, right? It keeps changing every 2 years with a new election. Even though many of the senators stay the same, there's differences in how these communities change over time. So this visualization was put together by my good colleague Jim Moody at Duke. And every one of the columns here represents a clustering of the senators in each individual two-year Congress, and then being glued together across time, so that what you can see is that the two groups get further apart from each other, and also a large number of senators who maybe aren't as well placed in the two dominant groups in the dominant two-party structure of the American Congress. They kind of like, we lose the middle over time as it becomes more polarized. But analyzing these separately is maybe not what you always want to do. So in this image, all we're doing is we're taking each one of these two-year columns, doing the clustering separately, and then trying to glue them together. There's a big piece of the network science literature that's been around for more than a dozen years now, called multilayer networks. And so the cartoon for it in the upper left here is, say I just have 4 different waves of data. So maybe it's 4 different time points, or it's 4 different kinds of connections. People might be connected to each other because they're friends, or they're family members, or they work together, or they go to school together. And so what you want to do in a multi-layer network, and if you're going to try to cluster the data in a multi-layer network into communities, is you don't want to just do each one of these waves separately. What you want to do is you want to use the information between them in an intelligent way. I could go down and give an entire hour-long talk about modularity for multi-layer networks. I'm going to not do that for you here. What I'll just say is that what it ends up doing is, now that you've got this additional structure, that you're changing either the type of connection that you have, or you're changing the network through time. What you have now is not one parameter, this resolution parameter that we had before, but now you also have a parameter that basically controls how sticky do you want the community assignments to be between layers. And so the formula here, with blown up in the number of indices that you have, I don't expect you to memorize, but the main takeaway from this formula is that the intralayer piece looks very similar, up to just changing some indices, to what we had a few slides ago. So we still have gamma floating around. But now we also have this extra piece, which is this interlayer identity arc. And this is just, again, sort of how sticky do we expect that if a node is put in a particular community in layer 1, how does that impact what community it's put in layer 2, layer 3, et cetera. And that introduces a new parameter. We've used this tool in some really great applications. Maybe one that's of interest to many people in the audience here is an old paper led by Danny Bassett back when they were a postdoc, and I had the pleasure of working with them on this. This is just a bunch of snapshots from that paper. The main takeaway from this paper was that we were able to use this concept of multi-layer modularity to partition nodes in the layers into different communities, to define a notion of how flexible was the brain structure of, as measured by fMRI correlations, of a bunch of subjects who were basically sitting in the fMRI machine playing a Guitar Hero-like task. And so what we measured was that they would come in, they would play this lab-based lab version of Guitar Hero while sitting in the fMRI machine. They would go away. They would come back for a future session. They actually came back for 3 different sessions in total, and they would play the game again. And there was just an absolutely fascinating correlation between this notion of how flexible their brain structure was, as measured by the fMRI correlations while they were playing the game, and how much better they got at the game, going from session 1 to session 2 and from session 2 to session 3. I've also had the pleasure of working with this kind of tool with some great political scientists. This is an international relations paper that was led by Skylar Cranmer and his then student Elizabeth Meninga. We used multilayer modularity to define a notion of how fractionalized the multi-layer network of countries who are connected to each other because they trade with each other and they have co-membership in different intergovernmental organizations together. And maybe they have a similar democratic form of government. And what's interesting here is how this multiplex, multi-layer modularity seems to have a significant causal relationship in a Granger sense with the total global amount of militarized conflict, even if you look out like 1, 5, or even 10 years ahead. I'm not the expert on the international relations of this, Skylar and Elizabeth are, but I thought this was just a fascinating use of the tool. If I go back to the Senate roll call again, though, now that I've talked about some of these other examples, before we were just talking about splitting one of those columns in the image at a time into the two communities. You can have a lot of fun with this data. You can go back and look at the entire history of the United States Senate since the founding of the United States. And so this is one of the attempts at visualizing. Again, I could probably talk about this image alone for an hour. What this image is trying to do is see one particular result of trying to cluster the nodes into communities. So a node in a layer here now is a senator during a particular 2-year period in the Senate. And so they might be colored blue at one time and colored green at a different time, or blue and green and red, because of course some of them are there for a long time. Of course, nobody is there, for the entire 200+ year period of it. But you just find a whole bunch of interesting structures in here. The big horizontal bars are an attempt to show the temporal period over which one of these communities lasts. So for instance, you see the very big blue bar at the bottom, seeing that the community we found that is most associated with the modern Democratic Party, goes all the way back to the American Civil War. And we've notated that blue bar with DR and other, that most of the members of that community, the instances of a senator in a 2-year Congress, was they nominally declared themselves as Democrats. So you can see the modern Democrat community, you can see the modern Republican community. But what I want to stress is this is one answer. And so I've talked a lot for the first nearly half of this talk about why some different reasons you might want to do community detection and see examples of it. But here I want to highlight that this was just one result of having picked that gamma parameter and that omega parameter. And you have to be really careful picking those parameters, because if you pick a different parameter, you end up going, and this is just a visualization of a different result now organized by what state do the senators represent. And you can see I only have 3 communities right now. I have a community associated with the modern Democrat Party, the modern Republican Party, and going back through a break point, the modern Democratic Party is lost to some party here colored in green. And this is totally expected if you know anything about American history, because it turns out that the Civil War was sort of a big deal. And if you go try to tell your political scientist friend that your tool lets them learn that, they're just going to laugh you out of the room, right? So you want to be able to pick these parameters. What's the resolution parameter? What's the coupling parameter in some more meaningful way? I also need to emphasize before I go further into this talk and to start hitting some of the takeaway messages and the tools of this talk, that community detection has just become an absolutely enormous area of network science over the past nearly 25 years now. And there are many aspects of it that I'm not going anywhere near today. There are a lot of great review articles. Some of my favorites are listed here. As one evidence of how big this field is, I like to point out that Santofortunato's 2010 paper is 100 pages in Physics Reports, which is like one of those little tiny print 2-column things. So, I mean, it's just an absolute tome. And of course, the literature has only expanded enormously in the 15 years since then. If you're interested in thinking about how community detection might be useful for your own data, I do encourage you to read this Case Studies in Network Community Detection paper. I'm very biased. This was led by a collection of then postdocs and grad students who were working with me. But we really try in that talk to talk less about the what and the how questions and more of the why questions, using a few key case studies from the history of community detection for why it would be useful to do this. So let's take a quick pause there and highlight a couple things for the second half of the talk, which is that as much as modularity at the default settings worked well on a lot of the examples that I showed you before, we need to acknowledge that modularity is problematic. If there's a, I mean, you can read a lot about this and how problematic it is in many different corners of the network science literature. It's a descriptive measure. It wasn't developed to be statistically principled in any generative sense. It only finds assortative structures. It's biased towards balanced communities. That is, if you look at the picture here, you see the Facebook example had a few communities that were all kind of the same size, and then a few other communities that were similar in size to each other. That said, despite all of its problems, modularity remains the most used method of community detection in most practical applications that I've seen. And I think that's largely just because there are many fast heuristics that are easily accessible across different computational environments in very standard and well-used libraries and packages. However, it's also frequently misused. And in particular, it's misused, I think, because these fast heuristics, there's really two issues. The fast heuristics introduce that there's a pseudo-randomness in solving the optimization problem to quickly find good solutions to what is actually an NP-hard optimization problem. So if you run it once, you get an answer. If you run it under the exact same parameters again, you changing the random seed, you might get a different answer. And so how are you going to account for the fact that you might get different answers? But you also have the problem that most of the packages typically don't make it particularly clear or provide much guidance about picking the resolution and the coupling parameters. And indeed, some of the common computational environments, the packages that are available, make it relatively difficult or outright impossible for users to modify the resolution parameter. They don't even know that they're misusing the method and that there should be a resolution parameter to sort of tune a knob and see, do I want larger communities or smaller communities? So our philosophy here for the second half of the talk is that if modularity is going to continue to be used very widely, we want to help people use it right. And to make these concerns and the approach here more concrete, I'm going to kind of start over. And I'll start over by saying that almost any story introducing community detection is almost obligated at this point to at least mention the so-called Zachary Karate Club. Zachary was a social scientist back in the, forgive me, I think it was the late 60s or early 70s, surveying the friendship network in a university karate club. So the best possible thing happened to Zachary, which was the club got in a fight. Not the regular sparring they do every night, but like they got into a fight where there was a disagreement between the president of the club and the lead instructor about what the direction of the club should be. And they broke up into two rival clubs. And so if you put yourself in this situation, if you've got a strong opinion about the content of the disagreement, then that's going to probably influence which one of these new clubs you join. But if you didn't really care about why the president and the instructor were in a fight with each other, you're probably going to go to the club that your friends go to. And so sure enough, that's what happens. So in this visualization, every one of the dots here is a person in this club. The edges between them are that they told Zachary that they were friends, and then the club split up, and it's split up basically perfectly according to this vertical dash line into the black colored nodes and the white colored nodes. And the extra dash lines are that if you happen to try to optimize modularity with the default resolution parameter, which is just that gamma is 1, you actually end up determining that it should break up into 4 clusters. So it works in this case, and that's nice. And this is such an overused example in network science, actually, that 15 years ago, when we were having a whole program year on complex networks back at SAMSI, the Statistical and Applied Mathematical Sciences Institute down in the Triangle where I used to be, Eric Kalakshik, who was the organizer of the program year, And actually, he's now your colleague there at McGill. He's the director of the Computational and Data Systems Institute now. Eric got so frustrated seeing people use this example and coming up with what was just a clear as day it should split like down vertically into these two rival clubs, that he finally, just in a moment of pique, said, if your method doesn't work on this network, then go home. I've since had the pleasure of giving him a t-shirt that has that quote on it and this image, but that's a story for another day. But to be clear about this data, so this is just a different visualization of the same data. In this case, maybe a single call of the function is going to be fine. So here I'm just demonstrating the typical user in R might just load up the data. This Karate Club data set is sitting in iGraph data, and they just use the tools inside of iGraph to split the community, split the nodes in the Karate Club up into communities. And it does a pretty good job. But this was Kalakshik's if your method doesn't work on this, go home case. And it turns out that there's some great work by Lito Peel and others that there's effectively a no free lunch theorem for community detection. There is no single one algorithm that is always going to be the best answer for how to do it. In this case, just almost anything you do will give you a picture that's similar to this, and that's great. But what happens if your case is more complicated than that? And in particular, the issue for us that I'm going to try to hit here in the remainder of the talk is that for most users who are focused on their application domain, they don't have time to be reading this ginormous literature of community detection and be, chasing every subtlety about alternative methods to modularity, what other codes they might be able to use, how to pick the resolution parameter. Again, most of them don't even realize, for instance, if you're running the code as written on the screen here, right, you don't see a resolution parameter anywhere. When cluster Louvain was called, just feeding it the data, the default was just that the resolution parameter was 1. And so, you can have a lot of smart people who are busy focused on the problems in their application domain. They're just trying to use this as a tool to study their data. And so surely we can provide some simple tools to them to help promote better behavior than just simple calls like this. I have to emphasize that there might not be any one single best way to do community detection because of the no free lunch theorem, but we can almost always do better than just this kind of quick set of commands like this. And importantly, this default gamma equals 1 resolution parameter choice, that might not be the appropriate scale to pick out the best communities. It's just the default used by most codes. So again, with apologies that I'm using a south of the border example, one of my favorite examples to demonstrate this is a network of college football teams playing what used to be called Div 1A American College Football. So this is from fall 2000. And so the force-directed layout here on the right, it's color-coding the football teams by their conferences. Every team is part of a conference. They play the vast majority of their games within the conference. They play a few games across conferences. So this is a natural kind of problem to have a strong community structure that you expect to be well aligned with the conference structure. But if we run the popular Louvain heuristic for community detection many times, so what I'm doing on the left now is I'm plotting for you what is the output of this modularity score versus the resolution parameter gamma. That's going to be the orange dots. I'm sorry, that's the red dots. And the orange dots, the vertical, is the number of communities that you found. So I'm just going to be crazy and run this 50,000 times. And so I ran it 50,000 times here at a bunch of different values of gamma between 0 and 6. And what you should see from this is that, first off, the orange points, there's a lot of noise, right? I mean, you see this big range and sort of when gamma is 2, 3, 4, it kind of flattens out a little bit, but there are dots at 11 communities, 12 communities, 13 communities. You should also note that if you go to the default at gamma equals 1, right, that's right in a region where, I guess I could be pointing it to you, right, that's right here in a region where nothing very robust seems to be happening. It's very sensitive in this range to small changes in gamma. The other thing I want you to notice, though, is this red envelope of points. So for every one of these 50,000 runs, what we're plotting in red there is what was the value of the resolution parameter and what was the modularity value at that point. And so you can see there are a lot of points that are not optimal, but there is a very well clear upper envelope to these points. And again, this is because the heuristics that are being run here are trying to solve an NP-hard optimization problem. So any given run might not actually find the global optimum. And so what we need to do now is we need to resolve these two problems at the same time, which is that there's a lot of randomness to this process, and we also have to figure out how to pick the right resolution parameter. And that's where we're going to introduce these methods to you quickly here with the remainder of the talk. So the first idea is CHAMP. So CHAMP is going to be sort of put in a cartoon like this. So CHAMP is an idea where what we're showing in the two pictures on the left, first, just a bunch of dots. So I'm already thinking ahead to the multi-layer case, even though a lot of what I'm going to show you today is examples on the single layer case. And so in the multi-layer case, you have both your resolution parameter and you have this interlayer coupling parameter. And so you might run the code at many different values of these two parameters. And so at each one of these values, you might get a possibly different answer. So this is just a cartoon indicating a bunch of different answers we got at different values of the two parameters. What we're going to do in CHAMP is we're going to take all of those answers that we found, and we're going to compete them against each other to find which one is optimum relative to that set for everywhere in the domain. And so what that's going to guarantee us is that we're going to get a bunch of different convex domains, and we're going to know which one of the partitions that we found is the best for each of the different possible values of the two parameters here.
Sorry, how do you define best here? Can you just clarify this?
I'll define best right now. So this is easy. That's a great question, because so we're finding our communities by optimizing modularity. So we're assuming that we should still, and this is a big assumption, we're assuming that since we were trying to optimize modularity, we better check, did we actually optimize modularity or not? Thinking back to these many red points here that are well below the curve. And so this is easier to visualize than just the one parameter setting. What we've got here now, the new picture on the right, is that every one of the partitions we found is represented by a line. And this is simply without, you can kind of see it in the details, but it's not unimportant to go into it, is that every one of these modularity functions was just a linear function in the resolution parameter gamma. And so each different answer, an answer is a partition of nodes into communities. Each different answer we found is a different line. And what we want to do is we want to use that collection of lines that we found. So we found 384 unique answers to this football network by running it 50,000 times. So we have 384 of these lines. Which line is the line segment on the upper envelope for what range in gamma? And if you do that, what you see is the picture here on the right, that there's a region where lines intersect. Every triangle is an intersection between two of these lines. But then there's a big region between these two triangles where there's one answer that is the best answer for that whole range of gamma. And then there's another slightly smaller but relatively large region here where that answer is now the best answer for that region of gamma. I'm old enough that my first car had an AM radio. I mean, that's really old school, but, and it was only AM, like there was no tape deck or anything. It was terrible. But like, you know, you'd have to sit and like tune the analog dial a little bit to try to like, you know, get in on the signal. And if you had a really strong signal, you could be a little messy with where you tuned to the knob and you could still hear the radio station. If it was a very weak signal, you'd have to be very precise in where you put it. So I like to think of this by that analogy of this is a very big signal here, that there is a split of the nodes. It happens to be into 12 communities. And then there is also very strong split here into 13 communities. But this is letting the data tell me, like, that's where the big robust signal is of trying to split these nodes into communities. And so now if I go back to the right, and now what I'm plotting with the line is actually the number of those communities versus in each of those intersections. So this was where I knew that it was 12 communities in this big flat region here, and then 13 communities right here. This all extends to multi-layer networks. I'm happy to point you into the direction of the literature and some codes for that. But in the interests of explaining the rest of the method, I'm going to sort of skip this, except for to say that, again, this is the picture now in 2D, because you have both a gamma and you have what is very commonly notated as an omega for what this interlayer coupling is, this stickiness of community assignments between layers. But yeah, so I'll skip the Senate. So that was the one big idea, was CHAMP. This is just a post-processing of the data to see, I ran a bunch of pseudo-random heuristics for an NP hard optimization problem. Can I clean up the answers that I got to be sure that for the many times that I ran it, am I looking at the answer that was the best at different values of gamma and omega? And what ranges were they? But there's another parallel idea that's just absolutely fascinating to me that we're also going to be able to leverage. And this is an idea due to Mark Newman a few years ago. And what he observed was that if I tool around with the algebra on what the formula for modularity is enough, you can actually make this look like a so-called stochastic block model. So a stochastic block model is a true generative model, statistical model for a random graph. And what you're doing when you fit a stochastic block model to your data is you're learning the parameters of the stochastic block model that best describe, in a maximum likelihood sense, the data that you have in front of you. And what Mark observed was that if he pushed around the formulae for the log likelihood of an SBM that was splitting things into K communities with just two parameters. There's a propensity theta in for how likely are you to connect to nodes in your own community, and a theta out for how likely are you to connect to nodes outside your own community. He was able to push everything around and make it look an awful lot like the formula for modularity, only now there's this big factor here, the differences of the thetas relative to the differences of their logarithms, that appears to be playing the role of gamma. And what Mark proposed was that you could now use this idea to try to learn what's the appropriate gamma for your data if you did it in an iterative sense. And again, I'm trying to avoid some of the details about how this works for multi-layer networks. Pamphilhouse and Lambiot and Porter did a whole big, beautiful work about how this extends to multi-layer networks, but the idea is the same. And so this is an attempt to visualize what happens if you use Newman's version of the procedure. So we're back to the karate club, because if your method doesn't work on this, go home. And in Newman's version of the procedure, he said, well, let's fix how many communities we're going to have. For the reasons of understanding the story of the Zachary Karate Club, maybe we're most interested in how this splits into two blocks. And if you do this, what's being plotted here is that if I, on the vertical, if I run an algorithm like Louvain or more recent methods like what are called the Leiden method, if I run it at a particular value of gamma, then I can use Mark's formula here for, I'm going to get an answer for my nodes into communities. I can use that answer to empirically measure all these parameters, theta in and theta out. And so then I can measure what gamma should that answer be associated with. And so it's an iterative procedure where you pick a gamma and you run. And in this case, if you just fix that it's going to split into two groups, it immediately jumps to a value of gamma that's somewhere around 0.78, 0.7, yeah, I think it's right around 0.78, 0.8, and tells you, well, that's the right gamma value. And you get the same answer there that you had when you ran it anywhere else. There's a subtlety here, though, which is that I had to know how many communities I wanted to split things into. I wanted to split it into two. And if you try to extend these ideas to a multi-layer network, think of that Senate example I showed you, where there are communities coming and going over the history of the US Senate. I don't have any idea how many communities I want to split that data into going in. And under the Pamphlet et al. Proposed iteration extending this to multi-layer networks, they let K vary. So there's much less consistency in the outcomes. In fact, even this problem, if you let K vary, and again, the vertical is what value of the resolution parameter do I start with, and then where does it jump to? What's being visualized here is that you can see that on average, there's lots of arrows pointing things towards the middle. And so what I'm trying to visualize is what's the first gamma you jump to, and then the blue dots are, after letting this run for a while, what gamma does it stay at? And the only takeaway I want you to get from this picture is it's pretty noisy. And in fact, this problem only gets worse in multi-layer networks. So Pamphlet et al. Have a whole beautiful set of things where there's an easy regime and there's a hard regime. Their method works really well. You can just kind of like compute an answer, jump forward, change your values of gamma and omega, run your tool there, jump forward again. The trick is that in some regimes, this becomes very hard. And if you're, the connection to the story here is that this goes all the way back to these pseudo-random results because it's a heuristic trying to solve an NP-hard problem. And so in the picture on the right, what happens is there should be an answer to this problem where the artificial synthetic problem was created so that it would have a correct answer for this value of gamma and omega. But if you actually try to run any of the heuristics at that value of gamma and omega, it jumps you off to a different value of gamma and omega. So because you don't actually find the optimal solution at that point. So the big conclusion to all of this is let's combine both of these ideas. So rather than just running an iteration where we compute a partition of nodes into communities, then we update our parameters, then we compute again there a new partition, and we keep jumping. Let's collect a whole bunch of partitions first, run this Champ algorithm. So now we know from the set of all the partitions that we computed, which one is actually the best one of those answers at every point in our parameter space. Now the iterative procedure is just, and I guess I could be showing the bigger pictures here. Now the iterative procedure is simply a map that takes you from, so for instance, this brown polygon right here is one answer that's the best answer in the cartoon for those values of gamma and omega. But if you compute the updated values from this idea from Mark Newman and from Pamphlet et al., if you try to compute the updated values of gamma and omega, then it's going to push you over into this region where the brown's no longer the optimal solution, but this pink region has an answer there that is the optimal solution. And in the cartoon here, I'm showing there's just arrows jumping from one solution to another solution. But two of these are particularly important because they're fixed points. They map to themselves. Now, I need to caution that that's not a guarantee that they're the best answers, because again, you have to keep reminding yourself there's a no free lunch theorem here. There's no one way to guarantee that that is the best way to handle all situations. But our claim is that this is a better way in many situations. So the kinds of pictures you get, going back to the karate club here, what we're going to visualize now is the number of communities at each of the different resolution parameters. And the arrows are taking you, for instance, if you compute that the two community solution is best in this range of gamma, but it turns out that if you compute Newman's updated gamma map, it actually jumps you to a value of gamma over here where the two community solution is not optimal anymore. It's the three community solution. And eventually everything goes to a fixed point here where it's a four community solution. To close this out, what I'd like to show you is an example. And so this is right out of the ideanet package in R. There's a whole very verbose vignette about running this on this football network that I told you about before. And so the way that you do this, if you sort of collect all the ideas we've presented you today, first you just have to run the heuristics many times. And so we basically just created a wrapper to what is the cluster Leiden function in iGraph. And so we're running this get partitions wrapper many times. Here we happen to have chosen to get 500 possible answers, 500 attempts, that is at 500 different values of the resolution parameter gamma, to partition these nodes into communities. And you can see the output says you happen to get 64 unique partitions if you run it 500 times. So now we run this champ idea. Again, the champ idea was just compete those 64 partitions against each other, thinking of them as lines that intersect, and extract which partition was the optimal partition. And you see this picture looks a lot like what we had before. And this is the graphic that gets created by the champ function in ideanet. And there are only 20 of these 64 partitions that are somewhere on that upper envelope. And then the last step is we ask, well, do these map to each other? And so yes, what you see here is that everything maps either up the hill or down the hill to that partition that happened to be the one I was talking to you about with the wide range of gamma values earlier, that happens to have 12 communities. Of course, I wouldn't be telling you about all of this as if it didn't also work in the multi-layer setting. The more interesting one is this hard regime of Pamphil et al. That I mentioned to you before, where if it were to do the answer right, it would get to this point here. But if you run the iterations, just rerunning the code at every value of gamma and omega, and you subject yourself to all the possible pseudo-random effects of the heuristics, you don't find the right answer. But if you run champ first on a large collection of networks, you find this big orange polygon here is one answer that is the true optimum relative to that set. It's just for various reasons, for quirky reasons of the heuristic, it's not one that it's easy for the heuristic to find at the correct value of gamma and omega that are most relevant to the generation of this data. So with that, I'd like to conclude. I know I'm out of time. What I hope you got from this talk today is that all this talk about community detection in networks, this is just a particular way of thinking about unsupervised clustering of your data of nodes in the network into groups. There are a lot of different methods for doing this. There is no single best way to do this in all situations. And the meaning of why would you do this? Well, that could depend a lot on your particular application. But our whole philosophy is that if these tools are going to be widely used, and in particular the modularity-based tools are going to be widely used, we want to help people use them right. We've made these tools available in both Python and R. The full multi-layer implementation is in the modularity pruning package in Python. But hopefully that will also be something that gets developed into the ideanet package in R soon. And we're really eager to help people use this. So please, if I can help you use this kind of tool on your data, I'd be excited to do so. With that, I'll just say thank you for your attention. I'd be happy to take any questions.
Thank you very much. Amazing talk. Lots of interesting threads. Questions, Anmar?
Really, really interesting talk.
Thank you.
So let me just lower my hand here. I have, maybe it's just a little bit unclear to me when you basically discuss this new methodology that you have with the finding the optimal code solution. I noticed that when you presented champ is that you could have also coexistence, like the number of clusters could coexist for the same value of gamma.
Yes.
So how do you, like when you're updating, every time you update in a given step, let's say that you have two solutions, which one do you choose? Like that's what I'm having trouble understanding.
Sure, yeah. So
that's number one. And my other question is, I'm a person that comes from dynamical systems. I'm interested in dynamics. Now, these clusters that you get, I mean, that could be a fixed time point. What happens as you progress over time? Like, I mean, you showed this senator, how it evolves over time. But, I'm interested, let's say, in bacteria, let's say, like, you showed the E. coli with the coexistence of these clusters. What happens over time? This is a transient phenomenon? Is it a steady state phenomenon, etc.?
Right. Oh man, those are all fantastic questions. So now let me see if I can unpack them. So the first one is a key piece of why, in fact, why do CHAMP and why combine CHAMP with this iterative map in the first place? Your comment about the coexistence. So if I go back to, this picture, right, then this is so the how many, why 11 communities and not 12, or why 12 and not 11? Say if you run these heuristics at a value of gamma of 2, right, you can see you get 11, 12, sometimes even 10 communities. And so this is one of the key pieces that makes modularity different than a lot of unsupervised clustering tools, is that you only have indirect control over the number of clusters you're going to get through this resolution parameter gamma. Rather than, I mean, you could, like Newman does when he runs his iterative procedures, you could say, I'm only going to look for the two community solution, the two community solution with the best modularity for the given value of gamma. But the traditional way that most of the heuristics are run, so if you just go call one of these functions in Python or R, it doesn't fix the number of communities a priori going in. You give it a resolution parameter, and so it's competing, say in the story here, the 11 community partition versus the 12 community partition at the value of gamma based on which one has the best modularity value. And in fact, there's sort of a whole history to like, why was it set up this way that is maybe not completely worth going into. But it's the way that the system is set up now, is that at any given value of gamma, it's competing the different numbers of communities against it themselves. And so now there's coexistence in the output of my 50,000 calls here on the left. But part of the whole point of CHAMP is that if I pick a value of gamma, only one of these answers of the 384 unique answers I got by running this 50,000 times, only one of those 384 can possibly be best, at any given, generically speaking, I guess, at any given point, except for the intersections, which are the triangles in the picture here on the right, where two of them tie at that moment. But just to the left of the triangle, one of them wins, and just to the right of the triangle, the other one of them wins. And so how do I make sure, if you like, CHAMP is like we call it a post-processing sometimes, because it's really just a cleanup. I ran it 50,000 times, I got 384 different answers, and this is my way of cleaning it up, and now I know which one of those 384 answers definitively is best, in the sense that it's on the upper envelope of this curve at every point in gamma. So that's one piece of your question. Now, I want to get to your dynamics piece too, but the whole fixing if you like, coming at this from a dynamics point of view, I won't call myself a proper dynamical systems person, but part of the point, I guess we'll get all the way here to the end. Part of the point of combining this CHAMP post-processing with the Newman and Pamphil et al. Iterative map is that what I've done is I've really taken a stochastic dynamical system and I've turned it into a deterministic one on a finite number of states, right? The only, if I run that football example and I have 384 possible answers, well, it wasn't even 384, right? When I ran, I only had 20 of these partitions, which were anywhere on the top. So if you like, from a dynamical systems perspective, the iterative map that's running on that is just an iterative map on a 20-state dynamical system where the states are just pointing to each other. And so what's happening is there's just one fixed point that is picking out, this is the one of those 20 possible answers that's a fixed point. Weird things can happen if you send it weird data. But most of the time we just get some number of fixed points. And that's the iterative map running on the champ set telling you these are really special partitions that you maybe want to go look at. Now, then your other question, your last set of questions about the dynamics of this. Oh yeah, the dynamics of this are, the Senate example. This is kind of part of why we built this whole multi-layer modularity tool in the first place, was trying to get a handle on things that were changing over time. And so, here you've got a network that starts with 26 people in the late 1700s who are connected to each other. And every 2 years, some of them cycle out and get replaced by other people. And the edges between them change because how similarly they vote with each other in that 2-year period might be different than in another 2-year period. And so this is an attempt to cluster all of that data at one time and see, is there some notion of assigning these nodes roles in the sense of who are they most connected to? I'm sure there's lots of different dynamical systems or dynamics kinds of questions that you could try to ask about this data that wouldn't, be addressed by this kind of tool. But what we're trying to see here is, from this kind of output on the left is, okay, legislatively, there's a modern Democratic Party, there's a modern Republican Party. If you work back in time, one of the things I didn't talk about because again, I could have talked about this image for an hour. The big gray bars vertically, those are the only time periods where briefly in those periods in time through the community detection, more than 2 communities were found at that time. And so there's this brief period in the late 50s and the 60s where there's kind of effectively, even though there's still nominally only 2 political parties in the United States, there's kind of 3 clusters of senators in the way they're voting. And again, apologies that I'm south of the border in my examples, but this is basically Republicans, Democrats, and Southern Democrats acting differently from the rest of the Democratic Party.
I guess probably nowadays you'll find four clusters. The extreme right, center, and maybe left.
You would think that. So one of the other flaws of this analysis is that it's because it's only really coming down to votes. And so if you did, I agree with your assessment, but it would have to be on a different kind of data that really touched on what are senators or members of Congress saying about different things. Then you would have to pick that up. So I don't know what you asked a lot of questions. So
this is perfect. Thank you so much. Yeah, you did answer it. Thank you so much.
They were great questions.
Yes, James.
I don't think I can hear him.
Me neither. So
is it
while James, yes, now we can hear you.
Okay. So thank you for your talk. That was very interesting and well described. I have 2 questions. One's a little bit shorter, and then the other one will be a little bit more open-ended. So the first one is, you suggested we could run it, say, 50,000 times, 500 times, but sometimes doing the clustering is quite expensive. So I'm wondering if there's a certain point where running CHAMP and these algorithms becomes less effective. Like, is there a certain general rule of thumb of what a lower level of runs would be? And then the second one is, you said that there's certain situations where modularity, it might not be a great metric. You mentioned the bias towards having equal communities. So if you could just kind of give like a brief sense of what sort of situations you might think, okay, maybe this isn't the right selection of tool, and then a couple like broad other kind of competing algorithms that you can maybe look into.
Okay, those are both great questions. One of the things that I really need to emphasize about both CHAMP and then layering this iterative map on top of the CHAMP answers is that both of these should be blindingly fast relative to the amount of effort that you put in, because you're absolutely right that sometimes the act of finding these communities can be quite expensive. The reason why everybody or not everybody, but the reason why these modularity-based tools are still very, very widely used, despite all of their warts and wrinkles and all, is that they are very fast heuristics. So like when I talk about running, 50,000 times on that football network, I forget what the time quote is, but I mean, it's laughably little amount of work computationally. There's a spot, and part of this is us not describing ourselves well in some of the papers. There's a spot in one of the papers where I think Ryan Gibson, who was the lead author on this iterative mapping paper on the champ set, I think if I remember correctly, he computes on the Karate Club 1 million times. And everybody's response to that is, oh my God, that's insane. Why do I have to run this 1 million times? Okay, well, first off, the 1 million runs took less than 5 minutes on his laptop. So if you're gonna that's like go and get a cup of coffee and come back and it's done, right? So, and it did not find 1 million different answers, right? It found lots of answers that are just copies with each other. Your question though is a really good one of like, well, how would I know when to stop? I actually think that's an interesting answer. I don't have a good answer for that. What I have observed in practice on a lot of data sets is, if I run it, 400 times, see how many unique answers you get. If you run it 500 times, how many unique answers do you get? Lots of times, I mean, this is maybe a very old school numerical analysis perspective. Like run it once, run the whole pipeline once, see what your champ plot looks like, see what these plots look like, that if I go back to, the kinds of outputs that you get. Lots of times what I'll do is I will run this once, having started everything with, here it was 500 runs, and I forget this just like runs super fast. I wish I could remember exactly how few seconds it is. And then I'll run it again with 1,000 runs. And if it doesn't substantively change the picture, I'm feeling pretty good about the fact that I ran it enough. If it really dramatically changes the picture, that's going to be a clue that maybe you needed to run it more times in the very first step, because everything hinges on what are the answers you find in the very first step. But the key thing I should emphasize here is that those second and third steps, they should be blindingly fast relative to the amount of time that you spend in the first step. And now, apologies, I've lost the thread of your open-ended question for the second part.
I was just asking, that was a great answer, by the way, but just about scenarios where you might have an intuition in advance modularity is not good.
Yeah, okay, so note that everything I have talked to you about today are what are called assortative structures. So in this picture, in this force-directed layout, each one of the nodes is a team. They're color-coded by what conference they're on, right? It's all very clumping. And my description to you about communities was that a good set of community assignments are nodes are more connected to within their communities than they are to the rest of the networks. Or when I gave you the adjacency matrices for the Senate, right? These have a big, strong block structure, particularly on the right, where there's, Democrats are connected to, they're in high agreement with Democrats, Republicans are in high agreement with Republicans. All of these modularity tools break down if you have a non-assortative block structure. So if you have, it's not a great example here, but I mean, right, if you have something that's maybe not a full bipartite network, but it's kind of tending in that way, right, you could think about, I'm making up this example on the fly, but, people giving talks to each other on a university campus, right? Like, well, professors teach grad students and undergrads, and grad students teach undergrads, and maybe the undergrads have an undergrad seminar and they give lectures to each other, and the grad students have an undergrad seminar and they give lectures to each other, and lots of people show up for the department colloquium. But there's a more complicated structure here. It's not just faculty talking to faculty and postdocs talking to postdocs and grad students talking to grad students, right? It's a much more nuanced kind of interplay and extracting the different roles that aren't just this purely assortative, you are more connected to people within your own community than you are to people in the other communities. In that case, the best tools you can use is just a straight out stochastic block model. I would steer you in that case. Which way do the slides go? I would steer you in that case in particular to GraphTool. Thiago Peixoto's phenomenal tool for it's the most efficient stochastic block model method that's out there.
Thank you. Peter, can you stay on for another 5 minutes, maybe?
Sure.
Okay, so I think those who want to leave can leave since there are students here as well. I think we'll just continue the conversation a little more, though people can stay if you're interested.
Thanks very much, Peter, for the talk.
And if you ever want to reach out and try this and it's doing anything funny, don't hesitate to reach out to me.
Fantastic. More questions? If not, I had several. I'll just ask one or two, not to keep them. They'll leave the rest for offline. More questions from anyone? So let me continue. Oh, yes, Monica, go ahead.
Hello. Thank you so much for your talk. You explain concepts beautifully.
Oh, thank you. Very kind.
I'm really new to looking at clustering of networks. And I just had a question. I literally was just playing around with iGraph the other day, so this is really great timing. You did mention using the lead-in algorithm instead of using the Louvain possibly.
Right.
And I'd love to know why, or like what are the differences, or if there's one you would recommend over the other, or if it's very like field, or like what your focus is based on.
Yeah, that's a great question. So they're very similar to each other, right? Leiden is basically a tweak on top of the ideas in Louvain and my accent on both are abysmal, but but basically the Leiden algorithm prevents a couple of the particular bad things that can happen in some extreme situations. The Louvain algorithm kind of grouping things in communities that should have later been split apart and things like that. But from a pragmatic standpoint, we lean very heavily into the Leiden codes that Vincent Trog, good, I've just left this slide up, and so I've got his GitHub listed there too. His Leiden codes that he's made available in both Python and R are some of the best codes available with the capabilities of giving them resolution parameters. And so that's the main reason why we lean in on both of them, in both the Python code and the R code, is just because we want to be able to access these resolution parameters. And my experience is that I've not run into a situation where the small additional overhead of Leiden has made things significantly slower than it would have been for Louvain.
Okay. Okay, thank you.
Oh, thank you.
Thank you. Questions? More questions? If not, okay. Let me yeah, was there a question? No. So thank you. That was great. I'm very naive to the field, so I was trying to work through conceptually. So I was wondering if there is a setup where the communities are non-exclusive, so I can be a part of more than one community interlacing. And secondly, is there a setup where communities are hierarchical? Because these clumps, they could have smaller clumps and then smaller clumps. So I was curious.
No, those are great questions. Yeah, so that's one of the things that, like, when I said I've skipped an enormous piece of the literature, yeah, overlapping community structures, obviously are better examples for a lot. You can tell yourself lots of stories. Modularity is a hard partitioning, not an overlapping partitioning. So, but there are tools that exist. I'm pretty sure there's something in GraphTool that allows for overlapping communities. Hierarchical communities is also something that I've thought a little bit about. In general, my experience has been that I prefer to have this knob picking out different community structures, and really all these tools, the champ tool and then running this fixed point detection on the iterative map, they're really just about highlighting some of the answers, so drawing the user's attention to them. If I run this football example again, and I don't know that I really need in the football example go find my, I don't know that I really need the iterative map step in the picture on the right to have me point out that that 12 community partition is really the one I want to look at, because it's already the one that has this giant domain where it's optimal in the middle here. And so sometimes we'll stop in practice, just you see the champ step and you go, okay, the partition numbered 27 here has a big range, 31 has a big range. Maybe I'm interested in 39 and 46 over here too, because they look like they have big ranges. But, it's then also kind of nice to just run the iterative map and see, oh no, that 12 community partition is really neat. My own preference at that point is to sometimes see, okay, if I highlight, that this 12 community partition is something I'm interested in, but maybe this 14 community partition right here is also something I'm interested in, then I'll go look under the hood and see that, in fact, everything you were saying was right. They are hierarchically related to each other. The 14 community partition is just two of the communities, and the 12 community partition broke up into two. If you know anything about American college football, it's because conferences have divisions. And so that's all that happened there. But sometimes I've like wanted a very hierarchically imposed structure. But in practice, I find that I kind of like the extra freedom of just letting it pick appropriate scales and then seeing how the scales relate to each other. Maybe on one scale, on one scale, the right way to think about American politics in the late 50s is Democrats and Republicans. But maybe on another scale, it's Northern Democrats, Republicans, and then a group that's Southern Democrats plus a few Republicans who ally with them. So that's a 3 community partition that isn't nested inside the 2 community partition.
Got it. So this brings me to the other thing that was puzzling me, which is the notion of a structural prior that you impose. So if you come with a structural idea, right, the hierarchical, so what you're saying here is that even if I don't have a hierarchical prior, it kind of drops out even if I leave it free. But I guess my chances of getting the hierarchical structure are greater if I have that structural prior, because I'm constraining the solution space. Now, if I have, usually this is my general question was, right, this is a statistical problem, but your talk was generally not talking about the statistical aspect. It was right. So you're getting unique solutions, but I'm wondering, is it overfitting, right? So the question is, how do you do model selection on this? If I start with a structural prior, I have 2 structures, I want to compare them. Isn't that the approach? I mean, just this is an open-ended question.
Yeah. No, that's a fantastic, I agree wholeheartedly that is the preferred approach. If you've got, because buried underneath here, particularly related to the observation of Mark Newman's that this is related to a specific stochastic block model. Modularity, I mean, I don't know that Tiago Peixoto would agree with me on this statement, but because he's written rather passionately about some of this. But the way that I think about it is effectively optimizing modularity was already, because of Mark's observation about what so-called degree-corrected planted partition it was effectively optimizing. It really is trying to find nodes into communities for that specific model. And so highlighting this fixed point, like in this picture right here, highlighting this 12 community partition, that's the best partition in this particular model sense. But that doesn't mean I'm going to necessarily throw away the 14 community partition, because I might still just be interested in like comparing and contrasting my possible solutions to each other. You ask a much more interesting question, which is, okay, like, what if I had multiple different models that I was trying to fit to this? And in that case, I really strongly urge you to go look at Tiago Peixoto's work. So that's the graph tool reference, because that's what Tiago's method is all about. It's about, but now it comes with a cost, right? Of like actually fitting data to a stochastic block model is a much more computationally intensive task than running these modularity-based heuristics, and which is again, I think why these modularity-based heuristics they get so much use is just they're easy to access and they're very fast. But if you do want to do this, the proper statistical model selection, then I urge you to go look at Tiago's tool.
Yeah, just one last question. This is because I'm completely naive, so I'm really looking for a tip or a pointer, right? So you talked about how fast these methods are, and this is you're searching through a large solution space, and this to me is what deep learning and AI. There's a lot of stuff on this, right? So I'm wondering, is there a methodology where people are trying to find solutions using some of those methods?
That's an awesome question. I don't know the answer to that. That's a good question.
I see. Okay. Perfect. I thought there would be that's like an obvious answer there. So okay,
yeah,
perfect. Okay, thank you so much, Peter. That was great.
Thank you. It was really my pleasure. I'm glad there was so much interest. Again, you know, if anybody tries to use these tools and has any issues with them, don't hesitate to reach out.
Fantastic.
Thanks so
everybody.
much, Peter.
Okay. Thank you, Peter.
Thank you
Bye.
again for the invite. I really appreciate it.
Bye.
Have a good day.